Dr. Liu. He is our mechanical engineering professor. He is currently associate professor in mechanical engineering, and his research area is nanoscale thermal science. And he is a really prominent researcher, and he won the outstanding dissertation award when he graduated. And he is also the recipient of the Outstanding Teacher Award and also the NSF Career Award. Okay, let's welcome him.
Thank you. Open. Hello. Thank you for the introduction. It's great to have deliver similar in our own department. So I'm Dr. Liu. I'm doing research in the heat transfer. Also teach a class in nanoscale heat transfer using molecular dynamic simulation. Right. Today, I'm going to talk about the research we did in the past year regarding about nanoscale thermal transport, and there's a terminology called Phonon transport. Right. So we understand Phonon transport in complex crystal, in organic systems, and in hybrid materials. So first of all, I want to make everybody on the same page that thermal conductivity is not an unfamiliar property. You're pretty familiar with it. We can feel it, right? So copper conducts heat well, plastics does not. If you look at this figure that shows the thermal conductivity versus electrical conductivity for the common materials at room temperature, we can see that thermal conductivity only expands the ortho magnitude of 5, and electrical conductivity expand the orders like 24. That means that at room temperature, thermal conductivity only have a very narrow range. So we need actually make our effort to expand this or extend this range for either lower thermal conductivity or higher thermal conductivity. For the same material, silicon, you can actually, through engineering method or find different structures of material, you can actually have very different thermal conductivity, right? For example, the natural silicon at room temperature is about 140, and you can have isotopically purified silicon have a slightly higher value. But when you make them as doped silicon or make them as nanowire or put them into nanograin or put alloy as the germanium, right, or make it amorphous, you're actually tuning it down thermal conductivity much smaller. So there's still hope for tuning the thermal conductivity even for the same chemical composition. Well, I want to do that. So one of the engineering challenges is actually solving the thermal management issues. If you have integrated circuit, and everybody's talking about three-dimensional stack integrated circuits nowadays, right, and also power electronics, usually it dissipates a lot of heat generated in this hotspot. And as in the integrated circuit, now people are talking about a few nanometers transistors. The nano hotspot actually generate much higher heat flux than ever before. So we need to spread the heat, connect them to the sink or whatever you use for liquid cooling, but you need a very high thermal conducting material to conduct the heat away, right? So that actually needs a lot of engineering to see, can we find better material which has higher thermal conductivity? On the other hand, you also need low thermal conductivity for energy conversion. For example, in thermoelectric devices, you want the thermal conductivity to be as low as possible to maintain its temperature gradient, because the entire thermoelectric energy conversion depends on the temperature gradient. So if your thermal conductivity is very high, then you don't maintain the temperature gradient. In some of the advanced design, you also want to have a thermal regulator where your thermal conductivity can be tuned on demand, right? So if I don't want this high temperature, I can say I will show a low thermal conductivity or high thermal conductivity. I can have a switch or regulate the thermal conductivity so that your heat flow can be controlled. So if we want to engineer all these materials, obviously you cannot use intrinsic materials, right? You have to go to a much smaller scale, like nanoscale, microscale, to engineer that. So that you need to understand the mechanisms for heat transfer. So what is the microscopic picture of thermal transport? As a lot of learn from other courses, maybe some physics, in gas, it's actually molecules. Those molecules collide into each other, right, bounce to each other, and that's how they transfer their momentum and energy. So the molecules is the dominant thermal carriers in gases. In electrons, in metals, it's actually electrons, right, because electrons dominant carriers in metals. So electrons carries the heat in metals. In insulators, we're basically based on lattice vibration, so we call this as phonons. Right? Phonons is actually the energy carrier for insulators. For semiconductors, you have both the electrons phonons. If you have a micro nanoscale thermofluid system, and then if you have the average distance of these phonons when they bounce into each other less than your characteristic length, then your Fourier's law will break, which is the bulk scale heat transfer law we all learn in heat transfer classes, right? So what happens to more complicated materials, for example, complex solids or in polymers or liquids, right? So this is actually the research direction we have there for many years. So let's look at the phonons first, right? So basically, this concept is actually from all this vibration. So if you zoom in all the material, you can see all these atoms that are vibrating, right? Apparently, there's no patterns here, but it can always do linear decomposition into different modes, right? So for example, I can decompose this seemingly random vibration to those 3 different modes and even many more modes. Each of the modes, they have a single pattern and single frequency. They could have very different frequencies between the mode, but you can see in each mode, every atom is moving according to a certain frequency and pattern, right? And this decomposition is not unique. So we pick one of the mode, and we can call it phonons. So that's the accurate definition for phonon, which is a quantized normal modes of vibration. As you can see, this is another typical phonon modes in diamond. You can see how these atoms move, how fast they move, and how they're moved, right? So all these atoms, lattice of atoms, molecules, they can uniformly oscillate at a single frequency. That's how we call it phonons in diamonds. Phonons, because we decompose it into many modes, they actually exist in different frequencies and also in different wave vectors because that's the direction it propagates. So if you put all these 2 parameters into a plot, as frequency as a y-axis, wave vector as x-axis, you can find that all these modes actually have very different features in terms of frequency and wave vector. I will put all the modes on one plot where we call this as a phonon dispersion curve, right? It tells you how those modes are different. As I show you in a previous slides that a random vibration can decompose it into many modes and show you 3 modes. And then here I show you the complete features, right? You have many more modes. And then some of the modes actually resemble the feature of acoustic waves. So we can call this acoustic modes, acoustic branch. Some of them are actually moving like an optical phase, so you can opt your phonons. So if you look at the details of the motion, acoustic mode, all the atoms are moving in phase, moving like this. And in optical modes, all the atoms are moving out of phase, they're moving like this, right? So that's some basic features of the phonons as the lattice vibrations. So if you want to see in a very detailed materials example, here I show 4 typical phonon modes in a 2-dimensional material, molybdenum disulfide, and I compute this so-called phonon dispersion, right? I pick randomly 4 modes, I label as mode 1, 2, 3, 4, and you can see the features of those 4 modes. Right? In a very acoustic branch, mode 1, you can see all the atoms are moving in the same direction, same pattern, with a very low frequency. Right? And then you can see mode 2, gradually, they have slightly different pattern and higher frequency, and 3 and 4, but 2 different atoms, molybdenum and sulfide atoms, are moving out of phase, and they are at much higher frequencies, because that's the point in the dispersion, which has a higher frequencies. Okay? Hopefully you can have better ideas about those vibration modes and phonon modes. So how can we bridge from those phonon modes to thermal conductivity? That's the material property you want to engineer, right? So there's a very simple theory that if we count each of the modes heat capacity C with group velocity, whereas how fast these modes can move, and the lifetime, whereas the average time those modes actually exist. If you add all this up for all the phonon modes, you get the thermal conductivity of the material, right? So you have to count all the modes to analyze thermal conductivity or engineer thermal conductivity. So a very simple example is that if for most of the material, the heat capacity and group velocity does not change with your engineering approach, you can simply change the lifetime. If there's more phonon scattering, right, or scattering at a surface, at a grain boundary, then your lifetime will get smaller and your thermal conductivity will get smaller. So you can suppress your thermal conductivity, right? So this is basically the theories we have. Based on this, we create an entire field called nanoscale thermal transport about 20, 30 years ago, because as you can see that you can actually manipulate this lifetime, then you can have your engineering characteristics length as well. So if you manipulate the L, which is the characteristic length of your nanostructure, it could be a thickness of your structure, could be a grain boundary size of your structure, right? Could be other significant characteristic length, L. And you have the so-called mean free path of your phonon, which is the same definition as all the energy carriers, where you have a lot of those interactions or scattering, and the average distance between this is called mean free path, right? So if your characteristic length of the structure is much, much higher than the mean free path, then you have a very classical or called Fourier region, where you have Fourier's law, right? So what we learned in heat transfer class is in this region. But if you start to shrink your characteristic length, you start to see that the L sometimes becomes comparable to your mean free path, right? So others may be still larger, but some of them actually long mean free path phonons will become comparable to L. And if you go, this is called mesoscopy region, which is in between, right? So if you go to ballistic region, where your phonon's mean free path is much higher, much longer than the characteristic length, you have ballistic region. In this region, your thermal conductivity will reduce a lot. So it really depends on the comparison between your characteristic length of your structure and the mean free path, right? Based on that, you can start to suppress your thermal conductivity, and you can engineer your thermal conductivity on demand, which is quite good. It's an opportunity here. So I would like to start from there to talk about the first topic, complex crystal, right? So for simple crystal like silicon, we now have understand that quite well. But a lot of complex crystals, actually, we still do not know the phonon transport mechanism. One of the crystals get interested over the last 2 years is called perovskite. This is the very typical structure of the perovskite, where you have these AB cations and the X anion, right? And the A ion cations is trapped in this. So this is the same structure as a lot of crystals as ABX3 structure, right? And then look at the very details, a very simple example of the BTO or STO. Those two all have the perovskite structure and what happens in the literature. Right? There's a large uncertainty in the literature. For example, if you look at the BTO's bulk thermal conductivity reported value, right? This is kind of a large range reported here. But if you look at thin films, actually all of them lies here. And what makes this worse is that when they actually have characteristic length to about 100 nanometer or 80 nanometer, it's kind of converged, right? So it's far from this bulk value. And also this converge is also different, right? So in this red square dots, you can see they converge about 60 nanometer. But for this blue one, I don't know where it converge, right? You could say they converge at 100 nanometer or even here. So it's really not consistent. The same thing happens to STO, where you have the bulk value predict here and here, but the experiment value is actually here and here, right? So neither the converge at the same characteristic length nor they converge to bulk value, which it should be, right? So there's a lot of problems in literature, even for those two very, very typical perovskite structure. And by the way, those two are also two famous ferroelectric materials as well, right? So we need to grow better crystal and also do accurate measurement of the thermal conductivity. So that's what we did. We actually collaborate with a professor in physics to grow very high quality single crystalline BTO films, and we confirmed that the structure is single crystalline and there's not many defects in it using a lot of the material characterization method, right? This is the XRD, this is read measurement, this is the TEM and SEM, and this is the AFM scan. Make sure that this is a very nice, high quality single crystalline BTO film, and we do our measurements, right? So to overlap with the last literature value plot here, this the green one is what we do, right? So those dots is what we measured in our lab, and this green dashed line is what we predict using computer simulation, right? So you can find that our data is much better than what the literature have, and also this converge with the bulk values we measured, right? And also this bulk value agrees with what literature reports. So this better agreement is because we have a very good quality of the film, accurate measurement. And this actually indicates that we can actually take advantage of this green dashed line to do more analysis because it's actually verified by experiments, right? So we did our own calculation and measurement, make sure that they agree with each other, with all literature. So now we can use the information here. So what we take from here is how the thermal conductivity is suppressed at different characteristic lengths, right? You can see it's actually start about 4 and continue to suppress at this length scale. So we can plot a design map out where if you want to know how to suppress your thermal conductivity, you need to reach a certain characteristic length, either using nanowire, nanoparticle, grain, right? So you can use that as a design map. And this is a map here. As we plot the map here, the x-axis is your characteristic length in nanometer, and the y-axis is how large is the suppression compared to a bulk value. That's what we want, right? Start with 100%, where you have a bulk value suppressed all the way down to 10%, right? So we put our work here, which is the black line, right? And we found this looks like very interesting that above 100 nanometer, you're almost reach 90 or 100% for a BTO material, which means the dominant phonon mean-free path is less than 100 nanometer. And if you take a look at 50% here, right, and then you can find that, it's actually less than 10 nanometer, which means that half of the contributor to the thermal transport is from phonons with mean-free path less than 10 nanometer, right? So we wonder whether this is the same thing for other complex crystal, especially perovskite. So we put all the literature data here. So those are literature data doing the calculations, and they have very rigorous calculations in recent years. We'll put them together. And we found that all the perovskite structures, or even all the complex crystals, share a similar feature where you have, right, I put a band here as a green line, where you all have this shape, which is very interesting because people previously think, oxide in its perovskite, they could have higher phonon mean-free paths, probably larger than 100 nanometer or even reach micron. But now we actually confirm that most of them are actually smaller than 100 nanometer. And then most of the phonons actually, or half of the phonons actually is less than 10 nanometer. There's a lot of indication to this, right? So if you have a structure that is more than 100 nanometers as characteristic length, you don't have to worry about the suppression of thermal conductivity. Or in other way, if you want to suppress the thermal conductivity, you have to make your feature size much smaller than 10 nanometer. Like make a nanowire, make a nanodot, make a smaller grain, right, nano grain. So that's a lot of information. So that's why we can publish in Advanced Science for this work with my recently graduate student, Enki. And we continue to do this because we already have this information, right? We know in this kind of perovskite structure, really, if you have structure larger than 100 nanometer, you have bulk thermal conductivity. So how can we suppress thermal conductivity further if we just have the structures with feature size larger than 100 nanometer? Okay, so we pick a very typical ferroelectric material to do this. This is the PMPT, whereas our Professor Jiang's lab actually has a lot of work on this. It's very good ferroelectric materials. You can change its ferroelectric domain walls on demand, right? So if you look at this material, they're actually composed of the two perovskite materials, right? So PMN and PT with certain fractions X. And then if we know that the perovskite's phonon mean-free paths are all smaller than 100 nanometers, so this domain spacing, if it's larger than 100 nanometer, so they're actually basically they're bulk materials. So how can we suppress thermal conductivity? It's only by those interfaces here, right? So that's the only way we can do. So we're thinking about, can we actually change the number density of those interfaces in its materials? And that's a good hypothesis because in ferroelectric materials, those are called domain walls, and we can change the number density of the domain walls by using electric field. So that's how we hypothesize this project. We want to take a single crystals, which is really large, like 2.5 millimeter as our study sample. And then inside of these single crystals, you have a lot of domains, where each domain means that the polarization is uniform. And between different domains, you have different polarizations. So we show these white arrows, right? And then those polarization basically is spontaneous properties of that domains, and those domain walls interface separate them. So if you use electric field to change the distribution or density of those domains, you are able to create a different thermal conductivity when you basically, we say, unpoled and poled with different method, right? Alternating current, we call it AC poling. And then if you have a constant current, we call it DC poling. So the objective of this study basically is trying to find out how can we maximize the thermal conductivity contrast using electric field. If you look at the literature, what we have so far, we can have much higher high thermal conductivity to low thermal conductivity contrast, but this only happens at very low temperature. In cryogenic temperature, those perovskite structures has been demonstrated that their thermal conductivity can be switched on the order of 5 or 3, but never happens at room temperature. For room temperature, what has been discovered before this work is all on thin films, right? They're really thin, like 40 nanometer or 100 nanometer thin films, and then the ratio they can achieve is about 1.1, and recently there's a larger value like 1.6 in PTO, but they're all in the thin films. So we want to really test our hypothesis in a bulk crystal, because bulk crystal is what we can really use as a thermal switch, right? So not at cryogenic temperature, actually at room temperature, and see whether this hypothesis is true, okay? And then that's what happens, right? My student actually bought those single crystal. You can see the photos and do the test. So they actually measure thermal conductivity along all the directions, and this measurement is under different polling, which we use AC current or DC current or voltage, right, to tune the properties. There is a D33 property we can use to monitor the extent of those tunings. So that's why I plot it as the x-axis here. And you can see that as we plot more and more, for example, here is ACP, the thermal conductivity normalized start from 1, right, start to increase all the way to over 20%, and then they actually decrease. This is very surprising. We expect a monotonic trend, right? So we think, oh, if we plot more, you should have more change. But now we found that it's actually increased and then decreased. This actually got us very interested in what happens here. What happens here? So we trying to understand how those domain, number of domain will change and distribution of domain will change, right? So we use the very established method called polarized light microscopy, PLM, to understand domain wall density change. Basically, this method measures retardation in light so that at the domain wall, it should have some birefringence. So we use that to determine basically the domain wall density, right? So this is the result. So if we take the unpoled sample and we analyze the domains like this, right? You can actually use MATLAB to count the size of domain, number of domain, and this is distribution. It's a well-distributed, like Gaussian distribution. You can fit the average size and the width, right? So the average size is 0.8 micron in the unpoled sample. And then if we poll to what we call ACP, which is the maximum, where the maximum thermal conductivity sits, you have the average domain size as 1.01, basically 1 micron, right? If you further poll this one, your domain actually get average size back to 0.8 micron. So this actually explains why you have a thermal conductivity increase and decrease, because it actually correlates with the domain wall, the average domain wall size. Basically, I also represent domain wall density, right? So this is actually a good discovery, because previously people think either domain wall grow larger or grow smaller, right? But now we reveal that, well, it really depends on the polling condition. You can get larger, and if you overpoll it, you get smaller on the domain size. So thermal conductivity can help you to understand domain wall as a very good indicator. So we're talking about thermal switch here, right? What about how it actually can be used as thermal switch, and then what's the reliability. So NCAKE actually did a lot of tests on using different polling methods like ACP, DCP, and see how the thermal conductivity can be switched repeatably, right? So you don't want a method that can increase thermal conductivity and suddenly fails, right? It can increase, decrease, increase, decrease. So we did a lot of cycle on different samples, actually 3 samples, and we did it on ACP and DCP. We found it's actually quite repeatable, and the maximum contrast does not show a big difference between ACP and DCP, and it's all about 25, some of them even reach 27%. So it actually confirms that it can modulate the material's thermal conductivity quite well. And remember, this is a bulk crystal. It's never been achieved in bulk crystal before at room temperature. So this paper is published in Advanced Materials this year. If you're interested, you can read the link here. So let me switch to the second topic, polymer chain systems. So complex crystals a lot of times are inorganic crystals. And then my research actually relies a lot on organic materials. So we think this is quite interesting because it's very less explored or studied. So very basic question is that we all know the plastics has very low thermal conductivity, right? Plastic basically is polystyrene or polyethylene. They're basically this structure, like carbon-carbon bonds. So you have carbon-carbon bond, but you have the lowest thermal conductivity, like 0.2 watt per meter per Kelvin. Well, if you look at the diamond, which is at the other end, that you have 2,000 watt per meter per Kelvin, but still have carbon-carbon bond. How can you have the same bond but have very different thermal conductivity, right? So that's always a mystery in the history. And then I think many years ago, Professor Gang Chen pointed out it could be possible that the polymer chain itself has high thermal conductivity. Just the way they pack together gives you low thermal conductivity. So there are some calculations calculate the thermal conductivity of a single chain. You also find that, well, the thermal conductivity of a single polymer chain is not low. It could be the same as diamond. It just, the way they packed, entangled together make them smaller, right? It's not intrinsically low. Can we take some information from here, right? Why is low? So we look at the polymer chains and polymers, apparently they're starting from 1-dimensional to 2-dimensional, 3-dimensional. So another work actually shows that very simple model, right? So if you have a single chain, 2-dimensional sheet, and 3-dimensional bulk crystal, calculate thermal conductivity, well-organized structure, you still find that the thermal conductivity of the single chain is higher than the double, a 2-dimensional sheet, than the 3-dimensional crystal. So, well, that probably because you have between the chain, there's a lot of vibration coupling, right? We call it phonon scattering here that decreases the thermal conductivity. Well, this is well known and expected, but this actually tells you that if you have a real 3-dimensional bulk crystal, your thermal conductivity also get decreased, right? Which is not very good to have high thermal conductivity, right? This is in polyethylene. So we think about, is there any polymer that can reverse the trend that you could probably have higher thermal conductivity in 3-dimensional than 1-dimensional, then you could have a high thermal conductivity for polymers we use in daily life, because you can never have 1-dimensional polymer used, right? Engineering approach. So if you cannot use carbon-carbon chains, can we use conjugated polymers? They have benzene rings, right? This is something new, something special. In benzene rings, you have those so-called pi-pi stacking between the rings, right? And if you have a benzene ring and other polymers or ions, you have other type of interaction. Would this additional interaction create some difference here, right? And we basically follow the same idea of a polyethylene, and we create a chain with benzene rings, look into their interactions, calculate thermal conductivity. We did find an opposite trend, right? So what we did is create a very simple benzene ring structure, right? Like PPP, they have benzene rings, have a chain, create 1-dimensional chain, 2-dimensional sheet, and 3-dimensional crystal. We use a molecular dynamic simulation to look into their temperature profile, calculate thermal conductivity, and we found the trend is opposite. So in this case, actually, you have a higher thermal conductivity in 3-dimensional crystal than the double chain, which is a 2-dimensional, than the single chain. All right, so this is completely reverse of the dimensionality trend in the past 20 years. People always think about if you have polymer chains, your single chain should be a high thermal conductivity. That's true when you have aliphatic backbone, which means you have carbon-carbon backbone bonds, right? But now we discovered that if you have a backbone with those benzene rings, it could be reversed, right? The crystal have a higher thermal conductivity. This has a lot of indication because three-dimensional thin films or materials is a real material we can use. So we really have the possibility to have higher thermal conductivity, even though not this high, but right, as a unit cell, and then you consider all the defects orders, they can still be high, which is already demonstrated in an experiment. So the reason for this is actually the suppression of the rotation, right? So if you have a chain that have a lot of benzene rings, because of those pi stacking, they have interaction. They will hold the chain benzene rings in a position. So the free rotation in those benzene rings has been suppressed if you have more chains in the surroundings, in the neighbors, right? So it's kind of like those interactions between the chains helps to stabilize those rotation, those chain backbones, which is helpful for thermal transport. We'll further discover another interesting, very, very counterintuitive fact is that everybody knows pi stacking and think these have a strong strength, which is true. Pi stacking has a higher interaction strength. But does this necessarily lead to a high thermal conductance? We find that it's not, okay? This high strength does not lead to a high conductance. How we find that is that we put two chains with all its benzenes, right? We calculate how the heat transfer across those two chains which have benzenes. And also, as a control, we calculate if you have a carbon-carbon chain, what is the conductance? We found that it's actually quite the opposite. The polyethylene, where you have carbon-carbon chains, right, conductance lies here as a function of the overlapping lengths. But the benzenes are all here. Right, this is about 3 to 4 times difference. The benzene rings actually have much smaller conductance, right? So as though you have a very strong pi stacking interaction strength, your mechanical property could be stronger, but your thermal conductance is much lower. So we further take this one in some of the design, probably I'll talk about later on, not in today's talk. We found a very low thermal conducting material based on this principle, which is actually solely from the simulation. Okay, so that's probably what we want to share for what we have in the past year for the organic systems. Now we switch to a hybrid organic, inorganic perovskite, right? So I did my first session as inorganic perovskite, then I did those polymer chains. Seems like they're just models, but what if you put them together? They can be real materials. If you put organic chains into those inorganic perovskite, you'll form this hybrid organic inorganic perovskite structure. They are real materials. They're used for solar cells, right? So those structure, basically, if you still remember the structures of perovskite like this, right? If you replace that inorganic atoms in the middle to a molecule or a chain, you're forming this so-called hybrid organic inorganic perovskite, right? So this structure actually has been discovered many years and has been demonstrated for solar cell applications, has been exceeding the silicon solar cell conversion efficiency, but they're not very stable, very difficult to handle, right? So people still continue to change the recipe. For example, they can change from 3-dimensional to 2-dimensional. Here, in a perovskite structure, if you replace that atom in the middle to a small molecule, you have 3-dimensional perovskite, right? But if you change this small molecule to a longer chains, now you have 2-dimensional perovskite, because now you have an inorganic layer and those molecules, and another layer and those molecules. So those 2-dimensional perovskite structure will have a stable structure, but also from a thermal engineer perspective, this could be very interesting because this is a very typical 2-dimensional structure which might have an isotropic structure, which might have a very low thermal conductivity along this direction. That is well known for 2-dimensional materials. Because this is like by combining these two materials, so you have a huge chemical space to engineer, right? So you can put whatever you want into the middle for 2-dimensional hybrid perovskite. And we actually tried quite a few of those. I want to discover something new, right? So we tried a lot of them, and students very hardworking to measure them. And also, this is our only regular materials, right? We also try some really special organic catalysts called chiral, right? Chiral molecules. So chiral molecules actually, I'll explain later, that they have some certain preference of your handedness, right? So you can see those two molecules are mirror symmetry, but they cannot combine together. We call this chiral ligands. Those chiral ligands probably also bring something new. Right? So we studied all this, and we put them into materials and spin coat them as a thin film. We studied the thermal transport. There's a lot of factors that can affect thermal transport. This inorganic layer has certain resistance, right? Those chains, as we model, they have resistance, they have thermal conductivity. Those interfaces between those chains also has resistance, right? So eventually we find this resistance is huge, right? So this organic interface actually determines thermal conductivity. Since this work has not been published, I can only show you some preliminary results where we measure a lot of the different ligands, some mixed ligands, some mixed with chiral ligands, and we found that the thermal conductivity, how they depend on interlayer distance, how they depend on those organic distance, and how they actually determines the packing and the thermal conductivity. So I'd like to show you later if those work and published. Okay, but during this study, we actually found something really interesting. Right? Remember, we incorporate chiral ligands into these molecules, right? So, like here, we have those chiral ligands here, and those are inorganic layers. And when we heat it, we measure thermal conductivity. But then we found something really interesting is that those chiral ligands, where they know they can form chiral phonons, right, the vibrations, they start to generate spin signals. But the spin signals also are alternating. So we found the effect called chiral phonon activated spin feedback effect, which is also published in this year. I think it's quite interesting to share today. So why we care this, right? So nowadays, everybody's talking about quantum computing and qubit, right? So we know that in transistors, it's actually the bit, right? So you have electrons as open and closed, right, the circuit. So you have 0 and 1. You will never have a state like this, right, in a bit system. Right, you can check all the CS textbook, you only have 0, 1 as a binary system. That's the bit. But in qubit, basically quantum bit is different because now you have different state. You have 2 levels, right? Any 2-level quantum systems, you have this superposition. So now you can access to different states like this, which is a combination of 0 and 1 in any angle, right? So in other words, if you have 2 qubits, you can create much more states possible than the bit. Right, so that's the sense of why quantum bit, quantum bit is more useful. Any 2 levels quantum system can be anything, right? So electron spin can be one of them, which is actually the electron spin up and spin down is an intrinsic property of electrons. Okay, so I'm pretty interested in this because a few years ago everybody got excited about quantum computing, right? And then we're looking into how we can have electron spin, but we're working on heat transfer phonons, right? It has nothing to do with spin, but can you convert phonon to spin? That's something we can look at, right? So if you check literature, there's already a lot of research on this. People actually form different fields. We're pretty familiar with the charge current conversion to heat current. This is a field we have called thermoelectric field, right? So you have a thermoelectric effect. There's a community doing all of the research on this. And there is an even bigger community doing the research between the charge current and spin current conversion. It's called Spintronics, right? And then in the past 10 years, there's a new community thinking about, okay, there is a gap here, right? How can you convert spin current to heat current directly? So they call this spin electronics, right? So this is a new community actually looking at the effect of the conversion between a spin current, where you have the spin as a current, and then heat current, where you basically have heat transfer, you have heat current, right? One of the famous effect, or the starting point of the spin electronics, is called spin feedback effect, where you have a non-metallic magnetic material here, right? And then if you heat it, put it into a temperature difference or temperature gradient with a magnetic field, you will generate spin current, okay? And again, why spin current is important, because that's actually our hope for another type of qubit, right? So we can do quantum computing. So in the spin feedback effect, we need a magnetic material. This has to be magnetic, and you need external field, right? Which is not difficult to have. It's just you're limited to magnetic material, magnetic field. And there's a lot of theory papers about why this happens, right? So one theory is that, well, you have a magnetic material with the X-ray field, you have something called spin wave or magnons, and they can couple the phonons in these materials, right? And so what, right? the reason behind this is that if you want to create spin, you need angular momentum. Everybody in our mechanical engineering or aerospace engineering, we know angular momentum, right? Is that when object actually doing rotating motion, right? They create angular momentum. Those angular momentum is also needed for spin because they're also doing those spin up and spin down. So you have spin wave, you have magnon in magnetic materials. You can convert its angular momentum to the spin. I'm not familiar with magnons or spin. I'm familiar with phonons. So I'm thinking, can we actually convert phonons to angular momentum and to the spins, right? Can we use non-magnetic materials? Because it's too crowded with magnetic materials and a lot of disadvantage of the magnetic materials. First of all, the Curie temperature, which is when magnetic material fails, actually decreases quickly with thickness, right? So for a lot of the applications, these very typical magnetic materials at very small nano size, these temperature drops, which means if you just heat it a little bit, when the feature size decrease, heat it a little bit, those thermal fluctuation will destroy your magnetization, right? Which is not what we want. And also those materials is not, well, some of them are earth-bound, but it still have to be magnetic materials. You need a source of angular momentum. If you don't use magnetic material, you don't have the source of angular momentum. Like I said, I'm not that familiar with this field, so I'm thinking about how we can use something we're familiar with to create this, right? So that's back to chirality, right? So the chiral object basically means that you have a mirror symmetry with these two, but if you overlap with them, they're not the same. Humans, actually, the left and the right hand is a very typical chiral objects, right? So those two, actually, you cannot superimpose because they are mirror image. In control, that the achiral object, they're exactly the same, right, if you overlap with them. So we have DNA that is chiral, and that's actually very, very interesting how the DNA is designed. And you can find that in all the human body, we just have one chirality, which is very weird. Okay, a lot of molecules actually can be designed as left-hand and right-hand chiral. So this is actually a starting point, right? If you have molecules, they can have chirality. If you put them into a two-dimensional material, what would happen? So think that if you have chiral molecules, you should have chiral phonons, right? So they bring angular momentum. If it's very hard for you to imagine what is chiral phonon, probably you can think about photons, which is light, right? We have linearly polarized light, which can be decomposed into a left circularly polarized and right circularly polarized light, right? So we all know that in optical materials, you can separate linear polarized light to circularly polarized light. Motion of atoms, the same thing. If you have linear motion vibration of atoms, you can separate them into left-handed and right-handed motion of vibration into chiral materials, right? And those chiral phonons can carry angular momentum, and then whether this angular momentum can be passed to spin, we don't know. We have to test. So to help you to understand how they vibrate, these actually are two very typical chiral phonon modes in PTO. You can see all these atoms, how they move, right? So they're actually moving in circles. And then if you have a mode 1, mode 2, they actually have a positive and a negative angular momentum, or they're just sign direction different. You can see how they move is actually the opposite, right? So they move opposite way. And if this is a bulk material, you know for sure they have angular momentum. But this is actually atom, right? But still much larger than electrons. So whether this circular motion, which we call chiral phonons, can pass this angular momentum to electron spin, we don't know. But we have a very bold hypothesis. It can, okay? So our hypothesis is that those chiral phonons, even though they're in atoms, they can pass the angular momentum to electron spin, create a spin current, which can be used in quantum computing, right? So this is our hypothesis, and how we do this is, well, it's coincident that we're looking into heat transfer, thermal conductivity of those materials, right? So we put this, implant these chiral molecules into those two-dimensional materials, forming something like this. And we spin coat this on a silicon substrate, and we cap it with a copper layer. And we shine ultra-fast laser on the top so that it will be heated, right? So that's the temperature gradient, how we generate in this layer. and we're using another laser to measure whatever happened on surface, right? So we have a special technique that can measure the spin accumulation on the surface. So one laser, you can heat the layer, another laser, you can measure the spin signals on the surface. So to test this hypothesis, this is how we set it up. It took us 2 to 3 years to really find our initial data like this, right? So we first did a control sample where you have a non-chiral materials in the middle. You have silicon, have a copper. The signal is 0 with some noise, right? And then we switch it to the chiral materials we have. Immediately, you see this signal is non-zero. So that basically proves our hypothesis. Once we found this data, we get really intrigued because it starts to oscillate, right? So it's not just like a steady DC signal. It's actually an AC signal. It can oscillate. So the oscillation is even more interesting because if you can generate an AC spin current, there's more usage in the quantum computing, right? And also, how they oscillate, whether it depends on chirality, right? This is a chiral S. If I change it to chiral R, which is left hand, right hand, well, the oscillation becomes different. Well, the phase of oscillation becomes different. We also did that. We changed the intercalated ligand from the left-hand side to right-hand side, and then we found that the rotation is opposite, which means the spin current generated one way is like this, another way is like this, right? The opposite phase. So that's why you see the signal, the phase is different, which means you can determine the spin current by how you implant this molecule, right? Which is easy because when you make this material, you can implant, say, I want this one to be left, I want that one to be right, and your spin current will be exactly like how you program them. So that's even more powerful in quantum computing, right? So to confirm this is from a spin feedback effect or from temperature gradient, also did some power dependence, basically give you different AC temperature, DC temperature. We found that they're all scales linearly with the different temperature gradient. That even confirms our thoughts, right? So we call this chiral Phonon activated spin feedback effect, where you have a non-magnetic chiral material here, and then you can have whatever the metal here, right? Without magnetic field, once this material is heated, you will generate a spin current. Right? So this is a very powerful. First of all, this is room temperature generation of the angular momentum of spin current without magnetic element, without magnetic field. So you can remove all this requirement about magnetic element and field, right? So as long as you have a chiral material heated, you will generate spin current at room temperature. So this can expand those quantum computing materials from cryogenic temperatures, whatever used here now, right? And the temperature gradient, of course, is a driving force. So if you have a larger temperature gradient, you have more generations here. Okay, I think that's probably approached the end of my talk. So a few remarks that in ferroelectric materials in complex crystals, we can use those domain walls to reduce thermal conductivity with external field. That could have a lot of applications in the thermal field. Also, those thermal conductivity can be used to understand the behaviors of those ferroelectric domain walls. In organic systems, we found that if you have conjugated polymers where you have those benzene rings, it provides us a lot of opportunities to engineer high and low thermal conductivity. We found actually 2 very counterintuitive effects, and we're working really hard to see, can we actually make experiments to demonstrate this? Can we find materials with higher thermal conductivity and lower thermal conductivity using these mechanisms? And then when we're doing the hybrid organic, inorganic perovskite materials, we found a lot of chemical space to explore high and low thermal conductivity. And also, excellently, we found that if the organic ligand is chiral, you have really a very brand new effect called the CPAS effect based on chiral Phonon. So that interaction gives us a lot of opportunities for the future room temperature quantum information science applications. So with that, I want to thank my own students, my lab, and collaborators, and all the funding sources. And thank you all. I'm happy to answer any questions you have. Thank you.
Thank you, Dr. Liu. So now it's time for questions from students, audience.
I'm not a student.
Yeah, that's okay.
Okay.
Your audience.
Yeah, so thanks for the very interesting talk. And for several questions for each part. One question for each part. The first part is about when you use the domain wall, increase the density of the domain wall to decrease the thermal conductivity, right? Basically, you're saying the domain wall will scatter the phonon.
Yes.
So actually, if domain A and domain B, the major difference is the shift of the oxygen atoms, right? Polarization direction.
Yes, yes.
So with that, the only difference in terms of phonon dispersion relation between those two domains, only optical phonon are different, right?
Yes.
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 The same. So that means you're scattering optical phonons.
Well, that's not entirely true because the scattering mechanisms is at the domain walls. There's a lot of strain. There's a lot of strains and maybe charges on the domain walls. So it's not really about the bulk materials in the domain and then how the phonon dispersion changes. It's really at the domains how those strains actually create a huge thermal resistance. So the lattice atoms at the domain walls is quite different. So they'll destroy all its coherent modes.
Not only optical phonon difference.
Not only optical phonon difference. Of course, yeah.
Okay. So let's say another assumption is I have the same density domain walls,
Mm-hmm.
but I only change the distribution of domain wall matrix.
Mm-hmm.
Will that affect? Same density.
Our hypothesis is that it really also depends on distribution, but we are testing it now. Actually, this is actually one of the hypotheses in the proposal that whether the distribution of the domain walls affect thermal conductivity. I think it depends on the spacing between the domain walls, right? Whether there will be correlated domain walls or whether there will be individual domain walls. If there are individual domain walls, probably they're just thermal resistance. So there's no correlation. The distribution probably is also not affect the final result, but if there have some interference effect, then the thermal conductivity will be different.
You're saying the distribution may be coupled with the size of each domain. Right?
Yes.
Size domain,
Yes.
Distribution doesn't matter. A nano-size domain distribution may matter.
Yes.
Or vice versa.
Yes.
Okay, the second question is the second part.
Uh-huh.
For the benzene, when you have bulk benzene, many layers,
Mm-hmm.
you have higher thermal conductivity, right?
Yeah.
So this, if I can transfer this idea to graphene and graphite, it seems to be vice versa. Graphene has a very high thermal conductivity, but graphite is lower thermal conductivity.
Graphene's high thermal conductivity is along the in-plane direction,
Yes.
right? And then they have those interlayer coupling to have.
It was in-plane, right?
Yeah. Graphene is in-plane and graphite is also in-plane. First of all, both of them's in-plane thermal conductivity are almost the same, right? So it's just really the cross-plane, and the cross-plane is really based on those interlayer coupling from the van der Waals forces, right? So I don't think that's actually will be different from whatever we studied here. It's a different story, right?
Each benzene layer is van der Waals or you have bond?
It's van der Waals plus those pi-pi stacking. So the pi-pi stacking automatically will have electric static forces.
Okay.
It's not just van der Waals. It's stronger. So that's the thing why it's interesting or counterintuitive is that if you have a stronger force, but you have a weaker conductance.
Okay.
Usually you have a stronger force, you have a stronger conductance, right, in most of the material systems. Okay?
Thank you.
Thank you for your questions.
Okay. And any other question? Then I have one more question.
Sure.
So you use the perovskite as a Polymer switch, right? So you pull the PMMPT and control the thermal conductivity, but the pooling state is also can be disrupted by the temperature.
That must be at much higher temperature. I think it's over 120 degrees C.
120 C.
Yeah.
Right.
Yeah.
So I'm asking you because my specific application is a high temperature, it's 125, 150 degrees C, and I want to control the conductivity. Then this thermal switch is not very stable switch in the high temperature.
Well, of course, you have to look at a different composition that has a different phase transition temperature, right? So this PMMPT specifically have about 130 degrees C. If you want to use them in a higher temperature application, then you'll fail, right? But there are other options for ferroelectric material that can work on higher temperature.
Thank you.
And similar mechanisms can be used.
Oh, which one?
I mean, similar mechanisms can be used, but different composition, of course. Yeah.
Any other question? Okay.
Okay.
Thank you, Dr. Liu.
Thank you. Thank you all.